Hi everybody, welcome to this webinar on the integration of renewable energies to the grid. Since we are expecting quite a few people today, this afternoon, if you're listening to us from North America, or this evening, if you're listening from Europe, we will be waiting a little while before diving directly in the topic of today, which are renewable energies and how to integrate them with the grid. So let's start first with a quick poll. We would like to know if it is your first time attending one of our webinars, so that we don't repeat too much if all of you are familiar to our webinars. So I will ask my dear friend and colleague Gonzalo, who is with me today. Hi, Gonzalo.
Hello, Christian. Good afternoon.
Good to have you with me again today. So I will ask Gonzalo to first show you the first poll. So simply answer to the question if you is the first time for you attending one of these webinars. This will allow us to better tailor our presentation. So the answers are coming in.
Oh, it looks like what we were looking at last night. So we have no 63%, yes 38%.
Okay, perfect. So then it will be worthwhile to do the background presentation of who we are, since the 2/3 of you are not familiar with our webinars. So speaking of being familiar with the webinars, I don't know if you are familiar with the GoToWebinar interface also, but just so you are more comfortable, you will see on the right side of your screen a few tabs, gray bars, that can be opened by clicking on the little white triangle on the left. And out of these tabs, the two that will be of most use to you are the chat tab, if you have to send us a request or something that is more problem related, you know, with your connection with us. Otherwise, if you have questions about the system, about the topics that we will be presenting, we would ask you to write them in the question section, so that Gonzalo can answer them directly if it's a question that is only of interest to you, or relay the question to me so I can answer for everybody to benefit from the question. That's it for the interface. What percentage of our attendees are online, Gonzalo?
How many things you have online? 28.
Okay, so it's about half of the people who have registered. So let's start with the presentation. Then we will show you what will be the program for today, and then start presenting the company. So if you want to switch me back to my PowerPoint, please, Gonzalo.
Yep.
Thank you. So for today, what is the program, the agenda? So we will start by presenting ourselves, presenting the company, Festo Didactic, and then we will look at how we design our learning solutions here at Festo Didactic. Then we will dive, this should take about 5 minutes just at the beginning of the presentation. Then we will dive right in to the main topic, which is integrating renewables in the grid. So we will first look at solar power, how this can be taught with our training system, then wind power, and finally how to integrate these two renewable sources into a home energy production system, either off-grid or on the grid, as we will see. In fact, there is only one demo that is written there, but there will be a couple of demos through the presentation. And we will finish that with a question period, but be aware that we are welcoming your questions at any point. So if you have a question, just write it in the question tab, and Gonzalo will relay them to me at different points during the presentation. So please don't be shy to ask questions. We like it to be interactive, as interactive as possible. So quick history of Festo Didactic. Back in 1925, Mr. Stoll, Sorry. Mr. Stoll founded the Festo company. So Mr. Stoll was based in Esslingen, which is close to Stuttgart in Germany. And he founded Festo to be a company that was to produce woodworking tools for the woodworking industry back then. 30 years later, a new technology was starting to crop up, which is pneumatics. And Festo started using these technologies in its own plants to where they were building the tools for their customers. And they also decided to start building these pneumatic cylinders and pneumatic equipment for their industrial customers also. So this is 1955. 10 years later, seeing all the new technologies popping up, and seeing how the technical workforce was struggling with these new technologies, Festo realized that there was a need for training the technicians to work with these technologies. And that's when they decided to found Festo Didactic, so the didactic branch of the company that was focusing on building training systems and training solutions to train the technicians of the industry. Then fast forward 50 years, in 2014, Festo Didactic merged with LabVolt, which was a Canadian-American company that was producing also training materials since the 1960s also, but more in the electrical engineering field, while Festo Didactic was more focusing on automation and fluidics. So by merging the portfolio of the two companies, we came up with a much larger offering in terms of technical training systems, which is why now in 2020, Festo Didactic is one of the main provider of technical training education in the world. What are our main fields of expertise with the different training systems and training solutions that we provide? Well, you have a quick glimpse here. So factory automation, process automation, fluidics, pneumatics, hydraulics, building automation, environment and renewable energies, as we will see today, electronics, electric power, which is related to the renewable energies, of course, industrial maintenance, communication and radar, and HVAC and refrigeration. So as you can see, we touch to most of the training fields in the mechanical and electrical engineering field. The picture you see here on the left is the building from which we are broadcasting today. So this is based in Quebec City. This same building is also housing the manufacturing plant where all the systems produced in Canada are manufactured. So this is both the office and plant installation. On the right, you see the picture of the training team from the Canada team. So from left to right, you have Gonzalo, who's with me as a co-pilot today, Francois Xavier, who's also oftentimes with me in these webinars, and finally on the far right is myself, Christian. Finally, in the center, Mr. Matthew Plourde, you see there is the product manager for the line of product that we will be looking at today. Now let's have a look at how we design our learning solutions. But before, do we have any comments or problems on the technical side, Gonzalo?
Nope, there's no problems right now. We can go.
Perfect, perfect. So since we've been doing that for 60 years, both in Germany and in Canada, you might understand that we have lots of experience in building these training systems for our customers, our school and industry customers. So to make sure that the systems we build will satisfy the training needs of the schools or of our customers, we always start from these needs. Okay, so we will first question teachers, industry specialists, and our own Festo experts, because we are also an industrial company. So we will ask them what should be the learning objectives for this new training system that we want to design. Then from these objectives, we will ask our technical writers to write a series of lab exercises that would allow us to achieve these learning objectives. Realize that at this point, there are still no equipment available, no system has been built. We are just thinking about the objectives and how to achieve these objectives. Then, based on these lab exercise definitions, We will come up with the equipment specifications that allow reaching these, achieving these exercises, and then the learning system strategy. And then finally, we will build the hardware based on this former analysis. Finally, the technical writers will write the final version of the manuals that go with the equipment. So then you are sure that what you get is a system that is perfectly suited to achieve the objectives that it was aiming for, and that the manual is also perfectly adapted to the system because it's been written from the system and by taking pictures of the actual system. Okay, so let's now look at the first topic for today, which is solar power. So we will look only at solar and wind power. Of course, there are other sources of renewable energies, but since the series of courses that we are looking at are part of our package, which is called home energy production, so we are focusing on the technologies that can be used at the house, at the domestic level. So, of course, typically wind or solar. So let's start with solar. So what you will, before diving into solar, first let me introduce you the full system. So all the courses that are available on the system that I will be using today to demonstrate how to teach these topics. So what you see here is the course tree of all the courses that are available on our EMS training system. Starting at the top, we have the most basic topics, starting from DC power circuits, AC power circuits, single phase, three phase, the transformers, single phase, three phase, the renewable energy technologies themselves, solar power, wind power. Then we dive into the power electronics, single phase, three phase, DC, to eventually arrive at home energy production, which we will be looking at together today. But you will also see that there are many other courses that are not related with renewable energies, like rotating machines, three-phase, single-phase, DC machines, power transmission lines, how to protect the network with numerical protective relays, and finally, at the bottom, the most advanced topics, which are smart grid technologies like SVC, STATCOM, HVDC, doubly fed induction generators. So each box that you see there is a separate course that has its separate manual and the separate modules required to achieve all the exercises that are comprised in the course. The boxes that you see highlighted in blue are part of our home energy production package that we will be looking at today. So the whole package comprises these 6, 7, 9 courses that presents from the basics up to how to set up a home energy production system. So let's start with solar power. So everything you will see in this presentation that I'm using here, and by the way, this presentation is available for download by you if you go in the one of the tabs I was telling you. One is called download. What's the name of the handouts? Sorry. So in the handouts tab, if you open this tab, you will see that there is a file there called renewable energies PowerPoint. So this is the PowerPoint I'm currently using. You can download it, and I suggest you do it before the webinar is over, of course. Everything that I'm showing in this PowerPoint from now on is taken from our manuals, okay? So these are really, really small, a small excerpt of everything that you will find in the manual. I'm just taking out the most meaningful pictures, okay, to show you what kind of information you can find in our courses, but everything, again, is extracted from the manual. So as you can see here, our course on solar power comprises 7 exercises, and know that each of our exercises are written by our technical writers to be achievable within a single lab period. So typically each exercise will take about an hour and a half, 2 hours to complete. So here you have, right in this course, 14 hours of lab experiments made available to you, all pre-designed, all pre-written. So starting with the diode, then the solar panel, the photovoltaic panel itself. So why do we speak of diode before? It's because a photovoltaic cell has lots of in common with the diode. So it's a simple introduction to the cell. Then we will start looking at the various parameters that can impact the behavior, the performance of a solar panel. So the effect of temperature on the solar panel, the effect of shading, the effect of orientation in relation to the sun, and finally the effect of the level of insolation, of illumination falling on the panel. So all of this will be studied, and on top of that we will also have an exercise to show the student how to store energy from the solar panels into batteries. So again, all these images extracted from our manuals. So as you can see, we will first introduce the student to the working principle of a photovoltaic cell, how it works with the semiconductor layers, the symbols that are used to represent a photovoltaic cell, the equivalent circuit for a photovoltaic cell, how to connect multiple cells in series or in parallel, depending if we want more voltage or more current, how all combined they will constitute a full solar panel. Then exercises on the voltage versus current curve of a PV cell with the maximum power point. So we will teach the student how to find the maximum power point, so how to extract the maximum energy from the solar panel by using a variable resistance, as we see in the schematic here. A diagram showing the impact of insolation on the performance of a solar panel. So again, these are only small excerpts from the manual. Much more is covered, but this gives you an idea of the amount of coverage in these courses. And what you see there is the solar panel itself that is part of our training system. So now I will switch back. We will switch back to the camera so I can show you the actual unit here, right here. So this is our solar panel test bench with the solar panel inserted in it, okay? So the test bench, which is the big black box, is not a required element, okay? It's not required to buy it. Most of the times the customer will buy it with the courses, but it's not required. All of the exercises in the manual can be achieved with this single module here, which is our solar panel module. Sorry, I'm not on the right camera. This is the one. So what you can see here is that we have these two PV modules directly here on this solar panel. So we have two modules, the upper module, the lower module. So this is for the student to be able to work with two modules, to connect them in series or in parallel and see the impact of that. How can they achieve the connections? Well, all the connectors required are here on the top of the module, as you can see. So we have the connections for our two modules here, upper and lower, so it's easy to connect them in series or in parallel. We also provide the variable resistance here, the rheostat, to find the maximum power point of our solar panel. And finally, we also provide 3 diodes to be able to either bypass a module that is in the shade or block the current from the battery to discharge through the solar panel at night. So all of this is covered, of course, in the manual. At the back here, we have the heat dissipator, because it's really important for a PV panel to remain at constant temperature, and this is also covered in the manual. So we will have in our test bench a fan blowing on this unit here to keep the temperature down. But then, of course, for the exercise where we want to teach the impact of temperature, we will turn off this fan and see how the temperature impacts the performance of the PV panel. Finally, on the top here, well, I forgot to mention also this thermometer. So there is a temperature display embedded in the unit here also. And finally, you will be able to go outside and point this to the sun to get various level of illuminations depending on how you orient it in relation to the sun. And to know the orientation in relation to the sun, we provide you with this little mask that you can put here in this hole, which will project a shadow on these inclination rings. So you will be able to know the inclination of the sun in relation with your solar panel. So to be able to go outside and do this, of course, it is useful to be able to mount this on a camera tripod, and that's why we provide you with this this hole here to mount it on a camera tripod directly. So again, the 7 exercises in the manual can be achieved with this single module, except for one, which is about storing the energy in battery. Then you need a battery or battery module or a comparable battery for your exercises. But to make it simpler to achieve all these exercises in the lab environment, we provide this solar panel test bench, where we insert the solar panel, and we have, as I was telling you, a fan. The fan here, which blows on the heat dissipator, and the halogen lamp here in the back, shining on the PV panel. Of course, the lamp and the fan can be controlled from the front here, as well as the various connectors to access the solar panel in the back. So for this module, I won't do any demonstration because it's really, well, pretty simple. We shine a light on the PV panel, measure voltage, current, power, and so the student learn slowly how this works. They shade a single cell and see the impact on the performance of the whole panel, things like that. So I won't do a demo of that because I have things more interesting and exciting to show you than doing simple current and voltage measurement on a PV cell. So let's go back to the PowerPoint. Questions?
Yes, Christian, we have 2 questions. From the subject that we are touching, are some of them available for Europe?
That's a really good question. I must admit that I was focusing more on our North American crowd today at this time, because I suppose that we don't have too many people from Europe connected at 8 at night. But if you are listening to us from Europe, yes, indeed, we have a version of this system that is CE certified. So this system is not CE certified. The version you see behind me here is our rest of the world version of the system, but we have a European version of the system that does not cover everything that we will see together today, because it's a newer system. This one has been in existence for 60 years, while the European version has been around only for 3-4 years. But everything about wind and solar is covered also with the European version of the system. But the last part, which is about the power electronics and how to connect to the grid by looking inside an inverter, how it's inside a chopper, how it is implemented, this section, it's covered, but not as much in detail. So we provide a commercial inverter and a commercial battery charge controller to do the same thing that here we do with transistors, basically. That's it. Thank you.
Thanks, Christian.
So let's switch back to the PowerPoint, please, Gonzalo. Okay. So now let's have a look at wind power. So here you will see that for this course, we provide 4 different exercises. Again, each of them being 2 hours in duration. So a first exercise, which is about the voltage versus speed characteristics of a wind turbine generator. Then a second exercise about the relation between the torque and the current flowing through the generator. A third exercise, which is about the power, electrical power that we can extract versus the wind speed that is blowing on our wind turbine. And finally, how to store the energy produced by wind turbines in batteries. So again, a few excerpts from the manual. First of all, of course, we explain to the students what is wind power, how it can be measured, and how can we extract this mechanical energy and transform it to electrical energy. So, of course, the impact of the cross-sectional area of our wind turbine, of our wind turbine rotor, has a huge impact. So the more wind we grab, the more energy we will be able to extract, and that's why we build them so big. And of course, also the wind speed will have a huge impact on the amount of energy that is contained in the wind. Then we go into a bit of mathematics to explain to the students how we can calculate, in fact, the mechanical energy contained in the wind. based on the cross-sectional area, the wind speed to the power of 3, as you can see. So we understand how important the wind speed is important, imports, yes, in the calculation. And finally, also the air density, rho, which depending on the content in humidity in the wind, will make the air more or less dense and have an impact on the mechanical power. Then we show to the students how to find, again, the maximum power point, depending on a specific wind condition, at which rotor speed will we get, will we be able to extract the maximum power out of the wind, and how this can be achieved automatically by a maximum power point tracking device. And know that in our wind turbine that I will show you in a moment, we do have implemented a maximum power tracking circuit that will make sure to charge the battery with the maximum energy possible taken from the wind. So the students will have in a specific exercise to trace these power curves that you see here. So they will try at different wind speeds and different loads on the wind turbine to be able to find the maximum power point for each of these different wind speeds. So here is the front plate of the module I was talking to you about, our wind turbine generator controller. And you will see on this faceplate that we, again, try to provide you everything required to achieve most of the exercises in the course. So first of all, we provide you with the 3-phase output from our asynchronous, permanent magnet synchronous generator that is inside the module that I will show you in a moment. And then this 3-phase output, you can connect directly on the right to the 3-phase input of the battery charge controller, which will take care of converting this 3-phase AC output to a DC input to a DC output to charge a battery, and will make sure also to track the maximum power point while doing so. So this is where our MPPT device is located. We also provide you with a diode bridge to rectify from a 3-phase AC to DC, and finally 3 resistive loads to charge the generator and see the impact on the torque and current. Let's switch back to the camera, please, Gonzalo, and maybe have a closer look on this module here. Perfect. So this is the same module as you can see here, the real module. Right now it is already pre-connected for the demo I will do in a moment. But you can see that I have the 3-phase output of my generator connected to the 3-phase input of the battery charge controller. And the output of this charge controller is going, of course, to the battery lower, as we will see later on. But I wanted to show you that this generator is simply a permanent magnet generator right here in the back. And of course, we need to make it spin to produce electricity. So to this purpose, we will use the dynamometer that is right to the left of this unit here. So this is our 4-quadrant dynamometer unit. That is simply a DC motor that is computer controlled, controlled by computer, and that we will be able to ask to behave as if it was a wind turbine or wind rotor connected to the generator. So we will see in a moment that with the software that controls this motor, we will be able to say, okay, emulate a turbine of this type with a wind of this speed blowing on it with an air density of that value, and it will, depending on the values we set to these parameters, it will behave accordingly and drive the generator here as if it was connected to an actual wind turbine. Okay. I think we're almost ready to go to the demo. Well, in fact, I could, yes, let's switch back. I will just show here, Gonzalo, how to control the wind turbine. So I will switch to the software here. Okay, so right now you have a view of our software LVDAC EMS that allows us to communicate with our system and control it from the computer. I will show you in an instant all the connections that are done, but right now know that I am currently speaking with the 4-quadrant dynamometer that I've just shown you, and I am controlling it from this window here, our wind turbine emulator window. So from here, you can see that, well, first of all, I can show you that it's not the only thing it can do. Here, I can select what I want the dynamometer to do. So I can ask it to behave like a constant torque brake or a prime mover brake at the constant, clockwise, counterclockwise, at constant speed or constant torque. I can also ask it to behave like a mechanical load, like a flywheel or a conveyor, so it can emulate different types of mechanical loads. I can ask it to do a speed sweep to analyze the full behavior of a motor, characterize the motor, and I can also ask it to behave like a hydraulic turbine emulator or wind turbine emulator. So this is the function I am using now. And when I select this function, you see that I have all these controls. So I can set the wind speed here in meters per second from 0 to 12 meters per second, which corresponds to about 40 kilometers an hour, which is the maximum speed you will accept on a wind turbine before it breaks. The air density can be controlled, the wind turbine type that you want to emulate here, a few choices, different choices, all of domestic size, of course, residential size. We are not emulating multi-kilowatt and multi-megawatt turbine, and that's it. So now if you look at the lower portion of your screen where you can see the 4-quadrant, well, in fact, I will cheat a little bit here. Normally, we always tell the students not to run the machine when it is powered, but here for the demonstration, I will open the panels to show you that when I turn on this wind turbine emulator, it will start making the generator spin. And you see here at the bottom that we have an indication of the current speed in RPM of our generator, the current torque generated on it. So you can see that there is actually a torque because I am connected to the battery charge controller and I am currently charging the battery. So there is some current flowing through the generator, which produces this torque. The mechanical power at the generator is 33 watts, negative because it is in generator mode, not motor mode, and the amount of energy, mechanical energy, that has been inputted in the generator from the start. And of course, if I change the speed parameter here, notice that the speed I am controlling is not the generator speed, but the wind speed. And the emulator starts spinning faster by emulating this higher wind speed. So higher torque, higher speed, RPM, higher power generated from the emulator. Any questions, Gonzalo, before we dive into home energy production?
No questions at the moment. We can get into the home energy production.
Okay. So let's switch back to the PowerPoint then. Okay. Don't be shy again to ask questions, people. We are there to answer as much as possible. So home energy production, this is where everything comes together. So if you remember the course tree that I've shown you initially, now at this point, the students should have covered, DC power circuits, AC power circuits, solar power, wind power, and also power electronics. So somebody was asking me if this system was available in Europe. Yes, except for the power electronics section. What we will be covering today, the power electronics section is not yet available in the European version. Okay, so this course, which is called Home Energy Production, is another one which comprises a few exercises, 5 exercises in all. So first one, standalone home energy production. No, so not connected to the grid, how we can set up a system that is off grid and still autonomous. Then single phase grid tied inverter. Now we connect to the grid and see how this can be done. Then grid tied home energy production, 3-phase, then using a solar or wind power inverter without DC to DC converter. Then the next exercise is with a DC to DC converter. And finally, the last exercise is about large scale energy storage, how to implement it in the smart grid. So for this exercise that we will be doing together today, I will just do the first exercises, the first exercise, which is not connected to the grid, so off grid. But it's simply to simplify a little bit the circuit and everything. And the circuit, as you will see, is already quite involved with a standalone system. So I didn't want to overburden the presentation with how to connect to the grid. But of course, we will be able to have a look. We will have a look, in fact, to how this can be achieved with within the context of the system. So again, excerpts from the manual. So home energy production, we are presenting the concepts of standalone home energy production, grid-tied home energy production, showing how the situation has evolved over the last few years around the world in terms of grid-tied home energy production connected to the national grid, helping the national grid producing all the required power. And we have an image here from, I think it's Sweden. I've never remember. Yeah, I think it's Sweden, where we see the situation how it was in the 80s with only major power plants, you know, over the map. While now today you have all these little dots, green dots, which represents the home energy produced at home, connected to the grid and helping the whole grid. We also cover, well, of course, the first exercise is about standalone home energy production. So we will present to the student the frequency and RMS value of the output voltage, operation of the voltage feedback loop, the power limitation circuit, the battery under voltage protection circuit. So all of this is covered in this first exercise. This image here is really important because this is the circuit that I have implemented behind me here. So starting from a renewable source, either solar or wind, you will take the output of this device and feed it to a battery, typically through a battery charge controller, which is not shown in the picture here. Then the battery is connected in parallel with this unit to the boost chopper, the goal of which is to bring up the voltage from the battery to a value required to achieve AC power at the expected voltage level. So for example, the battery is typically 48 volts. We need to boost that to 200 volts or so, 200, 210 volts, so that once it has gone through the single phase PWM inverter, it will come out at the other side at 120 volt AC, 60 hertz, of course, in the case of North America. Our system adapts to the your national grid. So of course, if you are in a country where it is 50 hertz and 230, 220 volt, the exercise would adjust the parameters accordingly. So we show here to the students how to calculate, in fact, the voltage of the DC bus. So what is the value of the voltage of the DC bus to achieve a specific AC voltage at the other side? So here, as you can see, for 220 volts, we would require a DC bus voltage of 345 volt. And what is the duty cycle that is required on our chopper to achieve this voltage? Well, we see that it is a duty cycle of 0.93. So all of this is presented to the student, how to calculate these values. Voltage feedback loop. So of course, we want to make sure that the voltage remains constant at the output of our on our DC bus, no matter what is the load, no matter what is the battery voltage or the output of our solar panel or wind turbine. So there is a requirement to have a feedback loop monitoring constantly the voltage of this DC bus voltage and reacting on it through this feedback loop, reacting by controlling the duty cycle of the chopper to maintain the voltage at the required level. So this is what is shown here, and we explain to the student the impact of this feedback loop, the PI amplifier, how to modify the proportional and integral parameters to achieve proper duty cycle control. Here we integrate the protection circuits that are also implemented in our solution. So two protection circuits, one to protect the under voltage of the battery. So we are constantly monitoring the voltage of the battery with the one of the voltmeters that you see there, feeding that to the protection circuit. And as soon as we detect that the battery voltage is getting too low, we will simply shut off the system to protect the battery. Same thing on the output side. If we detect that the output, the electrical output power that is drained from the system is too high, we will shut off the system to protect it from not over voltage, but over power. So here is an example of a circuit that is done in another exercise with the insulated standalone inverter. Insulated because we use a transformer between the DC side and AC side to insulate both aspects of the circuits. There are other circuits, of course, for grid tied with DC to DC converter, without DC to DC converter. So all of this is covered in the manual. So now for the demo that I want to do with you for the rest of the presentation is, here is the outline. So we will first have a look at the operation of the standalone inverter, then operation of the protection circuit. We will supply power to an actual load, and we will power it with a wind turbine in our case. We won't do it with solar panel because we don't have time to try both, but we will power the system with a wind turbine. So here is the circuit that we will be setting up. So I will leave it there and present you the connections, but first quickly go through it. So here we have the wind turbine, emulator connected to our generator with a mechanical link. The three-phase output here going to the charge controller that is connected to the battery to charge the battery. So as you can see, we monitor the current coming out of the battery to see how much power it provides, also the voltage at the battery. Then this is sent to our chopper, which will boost, as I was telling you, the voltage from 48 volts to the 200, so about 200 volt that is required. And then the output of the DC chopper will be fed to the inverter here, which is implemented with 4 transistors to create our AC, single phase AC output here that will feed our load here. And you can see that between the inverter and the load, we have a filter that is there to filter out the high frequency components from the output of the inverter to obtain a pure, well, not pure, but a clean sine wave out of the inverter. So now if you can give me a picture in picture, Gonzalo, I will show how this is implemented. Well, in fact, yeah, we would need the opposite. No, perfect, that's it. But with a zoomed out view here. Oops. No, just give me a close-up of the console, that would be perfect. Like that. Okay, so I've already shown you the first part where we connect the output of the generator. Then the battery signal goes out of there, goes into a ammeter down here, and from the ammeter output, it goes to the inductor here, down here, to filter out not to filter out, sorry, for our boost chopper. This is the inductor required for the boost chopper. And then we get to our IGBT module. So this module here is really important. Can I have a close view just on the IGBT, please, Gonzalo? So as you can see, this module comprises 6 transistors, okay? All of them can be controlled independently by its own trigger input here on the faceplate. So you could generate your own trigger signals and feed them to this input here to control each of these transistors separately. Since in this exercise we require 5 transistors, 4 to implement the inverter and 1 to implement the DC chopper, we are able, and we have 6 total in the circuit here, we are able with a single module to implement both the chopper and the inverter. So the 4 transistors here will be used for the inverter, and this transistor here will be used for the chopper. So coming out of our inductor, as I was telling you, we come here for the chopper circuit, and then from the chopper circuit, as you can see here, internally it's already connected and feeding. So the output of this DC chopper provides us with our DC bus, and this DC bus is fed as an input to our inverter here. The output of the inverter, which is our AC signal, is sent to a filter module at the top here, which I was talking to you about. So here is our filter that will filter out the upper end harmonics, and then the output of this is going to, again, a meter here to measure the current, and then back to the resistive load up here. So here is my resistive load, which will be used to emulate various loads on my circuit. So it's simply resistive load, and I can control the value of the resistance with these switches. All of that, I did not show you the battery. Sorry, I forgot to show you the battery. Really important at the bottom here. So here is our 48 volt battery that is powering the whole thing. And finally, in the center here, the most important module of all is our data acquisition module. So as you can see, it's named the Data Acquisition and Control Interface module. So in fact, yes, it does 2 really important things here in our circuit. First, it comprises 4 current inputs, 4 voltage inputs. So it will allow us to measure the currents and voltage in different points of our circuit. And as you can see, there are lots of connections right now to measure all these currents and voltages. So it takes the voltage and currents, digitize them, and send them through a USB connection that you see here. A USB connection sends it to the computer. Then the control interface part of the module will send the control signals to the transistor module right here through this cable that you see here. So this DB9 cable allows our control module to send the triggering signals to the transistor module, so the transistors trigger at the right moment. Okay, so let's go back to our software to control all that. Yeah, we won't need, I think, the picture-in-picture anymore, Gonzalo. It won't give any more information. So we have already looked at the wind turbine emulator. Let's look at the, whoops, it's down here. Let's look at our home energy production control. So this window allows me to control the data acquisition and control interface module and tell it which function I want it to implement. So right now I'm telling it to implement a single phase standalone inverter function, but again, this is only 1 out of 4 different functions available for the home energy production course. And there are many more function sets available with this unit, depending on which course you buy. But in this case here, as you can see, we have the standalone inverter, the grid-tied inverter, the inverter with low frequency transformer, and one with high frequency transformer. So we are using this one here. And for this function, we see the various parameters over which we have control. The output power limit. So I was telling you that the system can monitor the output power to protect it. So if the output power ever gets above 250 watt, the system will shut off. Same thing for the protection of the battery. If the battery voltage goes below 44 volts, the system will shut off. Then a few, you can set the output frequency, in our case 60 Hertz, but of course I could make it 50 Hertz if I wanted. And finally, the DC bus voltage command here, I set to 220 volt. Theoretically, it should be 200 volt to get 120 volt at the output of the inverter, but because of the losses that we have in the inverter circuit, I set it to 220 to get exactly 120 at the output. Perfect. So you can see here in the meters that I have the voltage at the battery currently at 51 volt, no current flowing, of course, because nothing is connected to the battery yet, no power. And then this here is at the load, so at the resistance, how much voltage and currents are at the load itself. So nothing there. And finally, down here is the power provided by the wind turbine. Of course, it's not spinning for the moment, so nothing. So first of all, let's start with our standalone inverter. Since it is connected to the battery, as soon as I start it, it will start producing AC voltage for my load, as you can see here. So now the load sees 120 volt AC voltage with a current of 0.7 amps for a total power of 84 watts through my resistive load. And we can see that all this power is provided by the battery because this is the power output from the battery, 99 watts. So you can see that there is some losses in the circuit. So from 99 watts, I provide 84 watts to the resistive load. So something like 10% loss here. The voltage of my battery and the current out of the battery. Perfect. Here on the single phase standalone inverter window, we can see that we have to achieve this 120 volt, to achieve the 220 volt DC bus voltage, I need to have a duty cycle of 79% here. And the battery voltage is again available there. So now let's turn on our wind turbine. We'll first start it with a slow wind. So we can say that right now the situation is like there is no wind outside. My standalone system has to rely solely on the battery power. So the battery is providing power to all the loads in my house. And now let's say that the wind starts blowing slowly initially at 4.4 meters per second. So we will see now that I start producing some power from my wind turbine. So we can see that only 5-6 watts right now are coming out of the wind turbine, but still at least it allows my battery to provide a bit less power. So now the battery is providing a bit less power because some of the power for the load is coming from the wind turbine. But if I increase the wind speed here, my wind turbine will produce more and more power. Oops, I went above what I wanted, like this here. Okay, so you can see now that the battery is providing almost no power. In fact, it's receiving some power, and all the power to the load is provided by my wind turbine. So right now the wind turbine is providing all the power required for my residential load. And then if the wind blows even more than that, at 10 meters per second, now not only does it provide power for my load, but it also provides power to charge up the battery. So right now, as you can see with the negative sign, the battery is being charged by my wind turbine. So the wind turbine is providing both power to the load and power to charge the battery. So all of this allows the student, of course, to clearly understand what is happening. And of course, we also provide tools like an oscilloscope for the student to observe the various signals. And I will show you, I will talk to you about what we see here. Okay, so what we see is the voltage and current at the load. So the output of our inverter, voltage in yellow, current in the blue. And here are the triggering signals, the control signals sent to the chopper to realize and not to the chopper, sorry, to the inverter, one transistor of the inverter to produce these sine waves. So the students understand how the varying width of this pulse width modulation allows us to produce a sine wave like this. Of course, this is after going through the whole courses on power electronics. So normally they understand that clearly when they get to this point in their studies. Okay, let me shut off this wind turbine because it's a bit noisy. Do we have any questions, Gonzalo?
No, we don't have any question at the moment. Everything is fine. Actually, the only remark we have is that the country that you were showing the map is Denmark.
Denmark, I wasn't sure. Yeah, I was hesitating between Sweden and Denmark. So thank you for correcting me. I was mistaken. Thank you. So that's it. One last point that I can, if you don't have question, that I can show you is the protection circuit for the maximum power. So I told you that right now the system was configured to shut off at 250 watts of output power. So I will just turn off momentarily my inverter to change the parameter here down to 50 watts and start it again. So let me shut that down here. So you can see right now that I am drawing my resistive load is drawing 38 watts from the system, and the system keeps running no problem because this power is lower than the maximum limit I have set at 50 watts. But now if I increase the load here, you will see that after a few seconds, the protection circuit will come in and tell me that I am, like here, that we are in an overload condition and will simply shut off. So now we are not providing AC anymore output to the load. We could do the same thing, of course, to show you the protection circuit for the battery under voltage, but this requires changing the wiring on the circuit, so I won't do that now. But I just wanted to show you that these protection circuits actually work fine. And as can be seen here in this schematic here, you can see that everything that is in green is the internal logic of our functions with the feedback loops to maintain the DC voltage constant and the protection circuits for the battery and the output power limit. Okay, so you've been a really gentle and a quiet crowd. Looking for the right camera, Gonzalo. Oh, is the camera dead? Yes, I think, was it powered? Yeah. Okay, so you've been really a quiet crowd, as I was saying. We like it when we have more questions, but no problem. Thanks to have been with us today. As you know, there are still other webinars coming up. So look at our schedule and subscribe to these upcoming webinars, one on process control, one on radar technology, coming in a couple of weeks from now. So it will be a pleasure to see you there again. One last poll I would like to ask you to answer, please, before you leave. We would like to know if we are doing good here and if what we're doing is of some use to our attendees. So please tell us if this was meaningful to you and useful.
Okay, all the answers are coming in.
Perfect. So thanks again for being with us. Don't hesitate to contact us if you have any questions. You have the email to write to us, send us questions. Be aware that you will receive a link to the recording of this webinar tomorrow at this time. In 24 hours, you will get automatically the link to the recording, so you don't have to request for it. You will get it. Thanks again for being with us, and see you next time. Bye-bye.